Hello, Flat Earth researchers, debaters, and debunkers. Let's have a look at this argument that you'll often hear from level Earth reality deniers that we should see the sun appearing to shrink in angular size, like we see this CD shrinking in apparent size as it goes off into the distance. This is an argument, of course, that comes up because we say that the sun appears to set due to the effects of perspective. Basically, the sun is going further away into the distance in a parallel line above the surface of the Earth, and this makes it appear to sink down until it reaches the horizon. So, of course, because perspective is essentially this increase or decrease in angular size for everything that we see in front of us, then, of course, this argument might seem to be a logical one to make. But it's important to remember or keep in mind that when talking about the flat Earth compared to the globe Earth, people are often referring to models rather than reality. Now, what we observe in reality does not change. All right, I've got to emphasize that. Nothing changes in terms of what we actually see when we look across, say, for example, a body of water from the beach. Nothing changes about how we see the world because we're all seeing it through our spherical eyes. And of course, perspective, the way that we see a horizon in front of us, this apparent convergence of the surface and the sky, is perspective. These are the so-called laws of perspective, if you like. So any observation, no matter what, is governed by perspective. Now, you can describe the effects of perspective in terms of geometry or trigonometry even. It depends on how much of it you're going to take into consideration. Now, a lot of time, we just don't think too much about the surface because that's just there. And we're always talking about these things that are going off into the distance above the surface. Even a ship is above the surface, it's on the surface. So the top of that will eventually appear to decrease until it reaches the horizon or goes beyond this point, this kind of band of convergence where we simply can't see anything beyond that. So when I say nothing changes, I mean that there is a horizon and the distance that we can see with any clarity to the horizon in front of us, or on the surface at least, doesn't change. So for example, if we are at our eye level is about 2 meters off the ground and we're looking directly across a level surface, then the horizon that we see in front of us is about 5 or 5.1 kilometers according to this spherical geometry, which instead of which we can use to describe perspective when we look across a level Earth, but that is then switched into this geometry for a spherical Earth. So really, I've been saying for years that perspective is the imaginary curve on the Earth. And so again, it comes back to what we actually see in reality. We don't see any curvature. We see that it is locally flat. And then, we don't see anything that would make us think that we are on the outside of a sphere. Because what we see is observably a level surface. And the horizon is always at our eye level. So that's reality. When you look straight ahead, and you can test this yourself or just go and find it. You get someone to stand in front of a body of water, preferably the beach, but it could be some, landscape, it doesn't matter. And then you take a picture of that person and you make sure that the center of the camera is at that person's eye level. And you will see that the horizon behind that person, the subject of the photograph, will be at the same height as that person's eyes and in the center of your camera's field of view or the photograph. Okay, so you can test this, and it's been shown numerous times that the horizon is an indicator of your eye level. It rises and falls with you, so it doesn't really move, but as I said, nothing changes. The distance with which we can see any clarity across the horizon is the same as the mathematics. That doesn't change. So the higher that we go above the surface, the further we can see across the level surface to the horizon, where the surface just becomes just too condensed in our vision to be able to see beyond it. So let's have a look at how the globe Earth is represented. We have to address this problem when it comes to talking about what we see in reality compared to the model. So you're probably well aware that the globe Earth model proponent will say level is perpendicular to plumb. I'm not sure if I have to spell that with a B or not, but it doesn't matter, you know what I mean. So, of course, on a spherical Earth, you've got plumb or down for any person on the outside of this circle to be toward the center of the circle. That's the model, that down is towards the center of the circle. And then your level is then perpendicular or 90 degrees to that plumb. Okay, this isn't a physical fact of life on Earth. This is just what is referred to as level for the model, so that you can then talk about going around this sphere and maintaining level. In the real world, level is horizontal, and of course, well, it doesn't matter where you imagine your plumb line to be, it's horizontal. So in this respect, this is correct. Okay, level is horizontal, and you can imagine it as perpendicular or 90 degrees to plumb. Nothing really changes there as far as how we perceive level at any given point. But of course, when you have this perpendicular horizontal line, well, it never, ever, ever meets the surface, does it? So already this model doesn't fit with reality. It doesn't matter how high or low you're above the surface. It doesn't matter what kind of scale you are talking about. Your line of sight, your horizontal line of sight, even if you consider it as perpendicular to plumb toward the center of the Earth, is a spherical Earth, is never ever going to meet the surface. So of course you have to end up doing something like that. You have a line like that for the observer to hit, for their line of sight to hit the surface. Or you sometimes see that they actually end up angling this person down, so they're no longer perpendicular to plumb, so that their line of sight kind of pitches down into this curve. Either way, this doesn't fit with reality whatsoever, does it? So let's have a look at what's actually happening in terms of, or how we can illustrate perspective on a level Earth, and keeping in mind again that nothing changes. After that, we'll have a look at some sunsets, and we'll discuss what's going on and why the sun doesn't have to shrink before it disappears behind the horizon. So this is a side-on illustration of how perspective works. Nothing changes in terms of what we see when we look across a level Earth. Remember that we're not looking down to a horizon, we are looking straight ahead. This is how we see reality. So one way we can illustrate this is, for example, someone up in a hot air balloon at about 200 meters above the surface, and that person's horizon will be about 50 kilometers into the distance. That's where the surface and the sky, or whatever level surface, it could be clouds below the observer and above, appear to converge in the distance. Okay, so we have this distance of about 50 kilometers from the observer when they are 200 meters above the surface. That will be that point of convergence. That's where they will see their subjective horizon across a level surface and in reality. Bearing in mind that surfaces are rugged, there are all sorts of other conditions that affect any observation, but that's how perspective works. So what we've got here is a ship on the surface at about 10 kilometers from the observer, way up here, 200 meters high in the air. So this ship will appear in front of that observer's horizon, and they will see all of this surface beyond the ship. But they won't be looking down. You might have to look down to the ship, but this point, 50 kilometers beyond the ship, will appear to be up as if it's followed this blue line. Yeah, so this is how we see the surface in our eyes appear to kind of ramp up. We know it's not doing that, but that's how we know that we're looking across a level surface. And we can tell from everything that we can see between ourselves and the horizon that this is a level surface. There's no bulge, there's nothing else going on apart from whatever is happening on the surface. So yeah, that should be fairly simple to understand. And we know that the higher up you get, the further you can see. Again, this is just due to perspective. So let's just compare that with this scene below, where we've got an observer at about a height of 2 meters above the surface, just standing on the shore of the water there. And according to the math, which is fairly accurate, because we are talking about converting spherical geometry, but it's spherical geometry for perspective, into where we should see the horizon. And so it's about 5.1 kilometers to the horizon for an observer that's just 2 meters above the surface. And so this ship that's 10 kilometers away, this same ship that was in front of the horizon for this person here, is actually going to be beyond the horizon, but will still appear on the horizon. So anything that's on the surface beyond this point here will still be quite visible until it does just get too small in angular size to see, or it gets obscured by haze or whatever. Now, of course, on the surface of the water, you have waves and swells and all sorts of distortion, yeah? This is another factor that you've got to take into consideration, because, again, angular size for perspective applies to absolutely everything that we can see. So it's the entire surface and the entire sky that appears to go towards this vanishing point or horizon. That changes in angular size as well. So any waves in front of us will appear quite large, and then they get smaller as you go off into the distance. But just as we saw with the CD, for example, the physical size doesn't change. So you can easily understand that a wave here at the 5 kilometer mark that might be a meter high will block off the bottom or more of a ship that's 10 kilometers away, and of course has decreased significantly in angular size. Yeah, that's obvious. That's just a logical thing. You take all these factors into consideration. And so just because we are low to the surface and the angle of incidence, you can call it, just like when you talk about reflections, there's a limit to how far we're going to see across this level surface, because perspective makes this, it just condenses everything. Yeah, I don't need to explain this too much, because you can see this for yourself. You just look across the surface and you will see clearly for however far you're supposed to see. And then the surface appears to get condensed. And the higher up you go, that surface will appear to expand. So when we get up to 200 meters above the surface, we'll see a lot more of the surface beyond the ship. But again, we're not looking down to this horizon point. We are always looking straight ahead. This is a representation of how we see the world in reality, and how our eyes interpret a level surface for us. The same as looking down a corridor or any other artificial thing that you can grab or look at, where if you're looking straight along, then everything appears to converge in the distance. All right? So just to be clear, what I'm illustrating here is we have a level surface on the Earth, and it doesn't really matter how high we are above the surface. This is just to illustrate how perspective works, or it's a side-on view of how we see the Earth and how we see the sun set. So the sun is at whatever height it is above the Earth. That's arbitrary. For models, it doesn't really matter. And the idea is that it takes a parallel path to the surface, all right? Okay, it may be curving around in a circle, but what we see locally is the sun going off on a path that is parallel to the surface of the Earth. And just as we see the surface appear to rise up to our horizon, which is the center of our field of view when we're looking straight ahead, or our eye level, then we see the sun or anything in the sky do the same kind of thing. So we have the sun's apparent path as it goes off into the distance, maintaining the same height above the surface as it goes off into the distance. So whatever our height above the surface, if it's 2 meters, then we'll see a horizon at about 5 kilometers in front of us. If it's 200 meters in the air, then we'll see a horizon about 50 kilometers in front of us. And that's where we see the sun appear to hit the horizon. So this is the sun's path. And just to point out that, of course, on the surface of the Earth, you've got land masses that will contribute to blocking off the sun as it goes off into the distance. Now, again, just as with something physical, tangible like the CD, the actual size doesn't change. So the size of this doesn't change, but of course in our vision it does appear to change in angular size. And this land mass beyond our horizon, whatever the distance is to that horizon, will not be seen, but it will still contribute to blocking off the sun. Okay, so these things only appear to change in physical size, but they will cast shadows. And if this mountain is higher than us, and we are, I don't know, 10, 20, 30, 50, 100 kilometers or 1,000 kilometers away from that island, and it casts a shadow as the sun goes beyond it, then we will be in shadow. So it will be dark for us. Okay, so anything on the surface that is above it will block off and create shade for us on the surface. Okay, and the clouds are the same. So the clouds are above the surface. Of course, they're at different altitudes depending on what kind of clouds they are, but essentially clouds are also parallel to the surface. Now again, they will appear to come down towards the horizon, and they will be like the mountains as well on the surface. They'll eventually contribute to blocking off the sun, which is above us. Okay, it's above the clouds, it stays above the clouds, it appears to come lower. The sun over here will appear to be lower than clouds here. It stays the same height, but because of perspective, it would have appeared to come down like this. Okay, so this all contributes to the view. People are very fond of using models with nothing resembling reality on them. But we've got to take all these things into consideration. Okay, so I hope that makes sense. Yeah, it shouldn't need too much explanation. Apart from to consider that we never get this view of the sun doing this across the sky. The sun always goes above us, or at least it arcs across the sky if we're not on the equator. For me, I'm here in Phuket near the equator, so the sun pretty much goes overhead. So does the moon, maybe a few degrees off, and so it goes off and sets in the distance. So you see my point, though. This again is just an illustration of how perspective works, and as you can see, we can use triangles, and when we use triangles we end up with angles that add up to 180 degrees. So we can play around with this, and we can also create a hemisphere with 180 degrees. So these, when you're talking in terms of degrees, then they're all interchangeable. You start talking about ratios, and okay, you can correlate them with distances, but essentially you then start working with numbers or geometric shapes that are interchangeable, whether we're using a triangle here to describe how perspective works, and we might then use trigonometry. Those same angles can be used to talk about it in terms of spherical geometry. Yeah, we still end up with these curves and things. Okay, so all of this is interchangeable, and it's just, if you like, if you're going to add angles and distances, again, nothing changes as to what's observed. So everything that we observe, the angle to the sun at any given time in any given location is fine. It's quite accurate. It's been done for thousands of years, or hundreds of years at least. Nothing changes there. Those observations are valid as far as I'm concerned, but we're still doing it all above on a level surface, and we are using the trigonometry or the geometry of perspective when looking across a level plane and converting that into this sphere. But it's a dome, if you like, a dome of perspective, depending on the observer and their height and all the other figures that will go with it at any given time. Nothing changes, okay? So that should be clear now. What appears to be happening in our eyes when we see the sun go off into the distance. This is the flat Earth perspective. Okay. So let's now look at some real sunsets and compare what we looked at and illustrated just now in terms of perspective, and consider that this is what we see the sun doing. Now, the whole point of this is to understand why we do not expect to see the sun shrinking any great deal in angular size when we are looking across a surface and we are not very high above that surface, because, as I said, nothing changes. So if we are not a very great distance above the surface, then the distance to our horizon across the surface will be relatively short. So at a short distance, maybe 5, 10, or even 50 kilometers, it's still not very far into the distance, that will cut off the sun or anything else that's in the sky going off into the distance above us. And that includes the clouds that you can see here, which in the distance appear to be resting on the horizon, but there will also be a large gap between the surface and those clouds, but we can't see it because they just appear much lower because they're further away. The angular size of everything is decreasing in the distance. Those clouds might be several hundred or several thousand meters high, but we can't see that height in such greatness because it's very far away. And of course we have a land mass in front of us a few kilometers away, which is also blocking off anything beyond that land mass. We can't see it because we don't have much height. If we gain more height, we'd see further across the surface. And so when we gain height, for example, let's say the sun has set and we gain height above the surface and we see the sun set again, we're not looking down this imaginary curve of a rolling spherical Earth to see the sunset again. Consider it as the same as when you're in a car or even in an aeroplane and you're going along and you look out at the sun while everything else is whizzing past you. Fences and trees and hills maybe in the distance are going a little bit slower, but everything appears to be going past you. But you look at the sun, and the sun always stays with you, doesn't it? As you're moving along, it just seems to follow you, right? The same as a reflection follows you. And you look at this reflection here. That reflection only exists because we are there to see it. And this is another crazy thing about what we see. We can see things reflected in the water that are way beyond the actual water. This goes for the moon as well. You might see the moon that's supposed to be about a quarter of a million miles away. Yet we can see the moon's reflection in water that's just crossing across the short distance in front of us. This, to me, is another indicator of just how esoteric and subjective everything we see is, especially when it comes to the sun and moon. You can't compare them with anything else. You can't compare the sun with any other light, and you certainly can't compare it with a tangible object like the clouds or something that is going to shrink in angular size significantly over a great distance. The sun is a massive light, whatever it actually is, that lights up entire continents at a time. Anyway, sticking to the point that the distance to the horizon based on our height doesn't change as far as all the mathematical equations that we've got to fit that. So here we're going to have a short horizon, a short distance to the horizon, and so the sun doesn't have a chance to change much in angular size before it gets cut off at the horizon at such a short distance. So let's just watch the sun get cut off in this very short clip, and then we'll have a look at another one. So off it goes beyond the clouds, yeah? So it hasn't really gone down, has it? It's just gotten further away. But because those clouds are in front of us, they block off the sun, even though it's still traveling away from us in a parallel height above the surface. We just can't see it because it's blocked off by those clouds. But you can see that it's still lighting up the sky here. But we, because we are lower than these clouds, we are now in the shade of those clouds. Those clouds are casting a shadow. So we ourselves, as an observer, are now enshrouded in darkness from the shadow. Yet we look up and we can still see the light that isn't blocked by the sun. Oh, sorry, by the clouds. It's still there. And we'll see the same effect happen here. As the sun goes off into the distance, I'll just pause it there to consider what's happening there. We can see a lot further. There are no land masses in the way, so and you know, our height above the surface is, well, it's not that high, but it seems to, maybe it's in a drone or something. But in the distance there will be clouds, or at least atmosphere or air that is dense and hazy. And so just as we saw just now, the relatively close clouds and the land mass cutting off the sun, we see the sun going to that point in the distance where it is going to eventually be obscured by things like clouds above the surface, but we can't see them because they're so far away, but they still do the same job. They still block off the sunlight, and we'll see again this wonderful effect here as we are in kind of darkness now. The clouds above us here are in darkness, but we've got this lovely glow, and we've got the sky still well lit above us. Not because the sun hasn't dropped down, it's not starting to go underneath us. It is just getting further away, and we are in darkness. So, you know, this is something we have to consider as well. The model for the globe assumes that the sun is 93 million miles away, and it travels all that time and space without any interruption, because it's apparently a vacuum, and then reaches us. But actually, in real life, the sun, or the sun's light, or any light, there's a finite distance that it can travel. Whether it's a street light and you see the glow of a street light, if you are under the street light, you will be lit up by that street light. If you are a great distance from the street light, you'll still see the light, and you'll see someone lit up underneath that street light, but you yourself won't be lit up under that street light. So you will be in darkness. And you put headlights on, and there's a limited distance, a finite distance to which headlights or any spotlight or even a laser can go before it's just not seen anymore. So abandon those assumptions that have to be used with the heliocentric model, that the sun's light will travel forever. It doesn't. Or you can't assume it. So you just take a look at reality, and you can see that here we have the sun's glow is reaching its limit, and again, it's only been cut off because of our height above the horizon. We could gain more height, and we would see the sun again. Not because we're looking down. Right, this is going to be a sunrise. And I'll just have a look at this and see if you can see where you think the sun should rise. Here's the kind of surface horizon that we see in front of us. But have a look at this. All right. You can, again, we've got things in the distance that are cutting us off. We're on the ground, so the distance to the horizon is very, very short, and the sun comes up, and you can see it's obeying the laws of perspective in that sense. And because the horizon is so close there, we're not going to see any dramatic change in the angular size. Boom, the sun's there, and it's starting to come towards us, and it will go overhead. Yeah, it's a fantastic piece of footage, I think. Now, this is a wonderful example of how we can often be tricked into being shown what is apparently this drop. You see this with boats that seem to have been half disappeared by this horizon that cuts everything off. And that is because this is taken at a very low level to the surface. You can see in the foreground here that the camera is hardly any height above the surface. So that's what gives us a very short horizon. It might be as much as 1 or 2 kilometers. And again, as we discussed, when you're looking at water, then there are waves that will appear to get smaller in angular size, but they might even be getting physically bigger as you get off into the distance, into these swells. And we then get this horizon at a very short distance. So these clouds, again, they are the kind of clouds that would be maybe thousands of feet above the surface before they even begin, and the tops of those clouds would be many thousands of meters high, possibly. Of course, they're far away, so they appear smaller, but they have been cut off by this very close horizon. And so this is, again, just a very subjective view, depending on how close we are to that level surface. We don't suddenly have curvature starting a few kilometers in the distance. It's just the surface is cutting off everything else beyond it, because that's how perspective works. It's impossible to make out anything beyond that. And this is quite a long piece of footage, because it's not a time lapse, but you can see how close we are. And again, the footage is zoomed in, so that sun is just, it hasn't physically gone down or it's not physically coming up, and we are not physically rolling around to meet the sun. It is simply coming into view at a height that's way above those clouds in the distance, and those clouds are way above the surface. It's just the way perspective works. And as I mentioned earlier, we only ever see the sun coming towards us like this, and then going overhead or going off into the distance from east to west. And this is because of that perspective effect, something getting closer to us and then getting further away. Whereas when we look at parallel lines, as we can see here, we've got this horizontal line of the surface, and we see birds going backwards and forwards above the surface. Because of our view of the bird, this side-on view that we have, they maintain their same apparent height above the surface as they travel across the surface. But if those birds were going off into the distance, then we would see them appear to get closer and closer to the horizon, wouldn't we? That's all a matter of perspective. So perspective isn't only this change in angular size, but it's also the point of view, considering the point of view of the observer. Now, this is a sunset. As we can see, this again is taken from pretty much on the beach. It might be 1 or 2 meters high, so we have a very short distance to the horizon. And so again, the sun will get cut off by that horizon way before it has any chance to change in apparent angular size. It won't just carry on going off into the distance to a finite point. And if we gain height above the surface, we would see the gap appear between the surface and the sun again. The sun would be at our eye level again, or it would, we would see it come up. We wouldn't have to be looking down. Of course, the photographers tilted the camera up here to kind of get the dramatic effect of the sky there. So we don't have an eye level horizon, but the distance to the horizon based on our height doesn't change. And this is again a lovely shot that shows that something very close to you can cut off the sun. So it should be fairly clear now what I'm illustrating here. And as we know, when we see parallel lines side on, then we don't see any change in the apparent distance between those parallel lines. Of course, if we can measure the distance between them, that will be consistent. And this is, of course, an illustration from the side of what the observer themselves are seeing. And this is what has been converted into an imaginary globe. It's exactly the same. We don't actually see this view, just as we don't see ourselves on a spherical Earth, but we can, just as we do with any other scientific experiment or test, is take into consideration the tools that we are using to make an observation or a measurement. And of course, to make that, we use our eyes. And so the way perspective works, or the way angular size changes over distance, is how our eyes work. That's how it is. And of course, as I said, the height above the surface and the distance to the horizon doesn't change from what's already been well established. It's just that the surface beyond the horizon that we see just continues to be level. And so a short distance above the surface means a short distance to the horizon. And that is why the sun gets cut off quite soon when we are quite low to the surface, and so the sun can travel off into the distance, and it's gone off over here beyond our horizon, where it might well change in angular size. And of course there is a lot of footage where the sun does appear to change in angular size. But if you take some footage from the ground and say, oh look, the sun doesn't change in angular size, well, all you've done is film a sunset that's just a few kilometers in front of you, rather than going up to a high altitude and then seeing if this greater distance that you can see the sun before it sets, and that would be, if you're very high, then the sun will set below clouds, because the clouds become your surface. If you're, say, 40 or 50,000 feet in the air, you still get the same effects of perspective. You still see the surface and the sky appear to converge in the distance, but the surface might well comprise of a level base of clouds. appearing to rise to your eye level. And so then the clouds themselves will cut off the sun as it gets further away. And so you will see the sun change in angular size as it goes off into the distance, if you can see far enough, if you've got high enough above the surface to be able to see the sun longer. But if you're low to the surface, then the horizon will cut off the sun very soon. It's not because it's a globe, it's just because of the way perspective works. And we know that if you look at this side on, we look at two parallel lines. We've got the surface here, and we've got the sun's path as being parallel to the surface of the Earth. If we look at it side on like this, then those distances remain the same from here to here. But of course, if I actually take up the position of the observer and I look along this line here, then these parallel lines will appear to converge in the distance, won't they? That's how perspective works. We know it is. We can test that anywhere. Okay, so it's as simple as that. It really is. The geometry and the angles don't change. The distances to the horizon don't change. It's just your perception. And as always, perspective is the imaginary curve. Thank you very much.